Hello, this is our project on the Benchtop NMR-enabled gram-scale chromatography-free process optimization for the preparation of the mofetil ester prodrug of mycophenolic acid. My name is Sarah Chang, and I'm a rising senior from Menlo Atherton High School.
I'm Ovia Srinivasan, and I'm a rising senior at Valley Christian High School.
My name is Kylie Yang, and I'm a rising senior at Archbishop Mitty High School.
So Benchtop NMR is an analytical tool that can be used to determine product, track reaction progress, and investigate complex multi-component mixtures. Our laboratory previously utilized 19F NMR spectroscopy for high-throughput reaction condition screening in the optimized synthesis of chromatographic analogs, trifluoromethylated pyrazoles, and to investigate the mechanism of the Bigonelli multi-component reaction. We also did it for the synthesis of other chromatographic analogs, machine learning like density functional theory-based chemical shift prediction, and to synthesize reduced berberine analogs. When it comes to synthesis, there is always a loss in product, especially in multi-step ones, as well as difficulty in producing scalable yields. In every transfer of material, at least a few milligrams are lost every time. In this case, aiming for a simple synthesis allows us to prioritize sustainable yields, where we are able to produce multiple grams of product suitable for industry operations.
When we mention chromatography-free, we are referring to column chromatography, which is used to separate your product from byproducts and other impurities. Our optimization does not require intermediary purification, which saves about 1 liter of solvent wasted per gram of material produced. Process optimization refers to our condition screening, where we desire to use more mild reagents to increase operational simplicity. Since compounds are made on kilogram scales in industrial settings, we would like to reduce financial and environmental costs and maximize yield.
And finally, just to break down the word prodrug, the prefix pro means before, and prodrugs are inactive compounds that become active later on in the body after metabolism. They can improve absorption, reduce side effects, and better target delivery. And we'll dive into this topic later on. So to give a brief outline of what we're going to be conversing over today, we'll go over mycophenolic acid, MPA, and its prodrug derivative, mycophenolate mofetil, and we'll introduce esterification as a key reaction for this transformation, starting with initial challenges that we encountered in direct esterification. After that, we'll discuss the optimized one-flash silation of MPA, followed by our experimental approach, including condition screening and qNMR analysis. And finally, we'll wrap up with conclusions and future plans for our project. Okay. So organ transplants have been an effective method at replacing non-functional or missing organs in affected individuals, but a recurring issue has been graft rejection. Our immune systems are trained to identify and destroy foreign organs, and for transplant patients, this immune response must be attenuated to prevent that transplanted organ from being destroyed by the patient's own immune system. So mycophenolic acid, also known as MPA, is a natural product derived from the fungus Penicillium stolonifera. MPA is widely used for its immunosuppressive effects, mostly to prevent graft rejection in organ transplantation, and it is one of the 3 immunosuppressants involved in the most common maintenance regimen for patients recovering after discharge. So as shown in the protein model in the bottom right-hand corner, MPA in green is a non-competitive inhibitor of the enzyme IMPDH, shown in orange. IMPDH catalyzes the conversion of just to clarify, the enzyme IMPDH in blue and the conversion of IMP in orange to XMP, which is one of the steps in the synthetic pathway of dGDP, an important precursor for DNA replication. So MPA activity is specific for lymphocytes, which depend on DNA replication for proliferation during the immune response. They do not have a salvage pathway for DGDP synthesis, unlike other cell types. Therefore, MPA is 5 times more potent towards type 2 IMPDH, the isoform most common in lymphocytes. And MPA effectively halts the cell cycle of lymphocytes at the G1S checkpoint, and the unwanted immune response is attenuated too. So expanding on what I mentioned earlier, prodrugs are inactive compounds that are metabolized often in the liver and are cleaved into their active form, usually through enzymatic reactions by esterases. They're designed to remain chemically stable as they're metabolized and as they pass through the gastrointestinal tract, also known as the GI tract, and then are delivered to release the active drug. This, for one, can improve absorption, 2, extend the drug's duration of action, and 3, enhance tissue targeting, all while reducing side effects for the patient. And overall, prodrugs help exert a more effective therapeutic response, improve absorption throughout the body, and optimize bioavailability, or how much a substance is actually utilized by the body after it is administered. And so our lab has observed that esterase-cleavable prodrugs such as Tamiflu and benazepril can generally be used to overcome poor pharmacokinetic properties. They can be cleaved to produce the active form of the drug and can be chemically stable in the GI tract until bioconverted by enzymes, including esterases.
This has been applied to MPA in the preparation of mycophenolate mofetil, the FDA-approved ester prodrug derivative, which was made to enhance the bioavailability of MPA by about 90% compared to pure MPA. In the intestines, MMF is converted into MPA and morpholines by human carboxyl esterase 2, and any remaining MMF escapes through the portal vein into the liver and is broken down by human carboxyl esterases 1 and 2. However, initial attempts at direct esterification of MPA were unsuccessful, which led us to hypothesize that the acidic phenol is a competing nucleophile in the carboxylamide-mediated acid activation. While most phenols have a pKa of around 10, this particular phenol is about 100 times more acidic due to resin's donation into the lactone ring. This competing pKa makes it a potentially competing nucleophile. To prevent issues with the competitive pKa of the phenol, we resolved to protect MPA with a tert-butyl dimethylsilyl chloride group through a two-flask, two-step procedure previously reported in literature. In this procedure, we first doubly silate both the phenol and carboxylic acid before purifying the reaction mixture and transferring it to a separate flask where the carboxylic acid is then deprotected and left available for later EDC coupling. Through this procedure, we produced a yield of 35.69%, and since multiple purifications were required, it was atom uneconomical. While it may not be apparent to those of you who are not synthetic chemists, the larger strain of atoms in large-scale chemical processes, such as early-stage protection, are not the reagents but rather the solvents. As we purified our reaction mixture 2 times, we used about a liter of solvent per gram of material produced. And while this may not pose a significant issue in a small-scale academic fume hood, on the industrial kilogram or dozen of kilogram scale, this poses a significant financial, environmental, and atomic cost. Also, as the multiple purifications required multiple transfer of the reaction mixture, the yield variability was increased, making the procedure less scalable. To resolve this, we optimized a 1-flask, 2-step monosilation of MPA. In this procedure, we first doubly silate the phenol and carboxylic acid. However, we deprotect the carboxylic acid in the same flask using formic acid. Through this procedure, we obtain a yield of 76.3% and reduce the number of purifications required. By only purifying our reaction mixture once, we also reduce the number of transfers, making the procedure more easily scalable. As a result, we have been able to synthesize mono-siloxy MPA on a 3-gram scale. With this mono-siloxy MPA in hand, we synthesize our first MPA ester analog, 2-methoxyethanol. and we predict that human carboxyl esterase 1 will be most selective towards this analog due to its relatively larger acyl group and smaller ester group. This analog is composed of the same starting material as mycophenolate mofetil, but the ester functionalities differ.
So once we acquired the PA, we then performed EDC coupling in the presence of DMAP and dichloromethane and successfully obtained a pure silated 2-methoxyethanol analog as shown by NMR on the bottom left and LCMS on its right. We then attempted to deprotect the siloxy ester and we tested a variety of acids. When tosic acid was used, the ester decomposed back into its starting material. When formic acid was used, we did obtain our desired product of structure 1.5, as shown on the right. However, the reaction was insufficient, requiring several hours of stirring, and we did not obtain enough product to quantify yield by NMR. And when hydrochloric acid was used, we discovered that a highly polar product resulted in a highly polar product, as shown by TLC. And we hypothesized that the strong acid had popped open the lactone ring of the molecule, as shown in structure 1.6. Instead of testing another acid, the next condition we plan to test is tetrabutyl ammonium fluoride, which we hope to obtain our desired product of structure 1.5. The deprotection would occur through the formation of a silicon-fluorine bond in a fluorosilicate phenoxide exchange.
In addition to screening deprotection conditions, we screen esterification conditions to see which will allow us to form the mofetil ester seen on the right.
The Skeglich esterification is a well-known method for synthesizing esters utilizing a category of compounds known as carbodiamonds. It can be run under mild conditions such as room temperature and involves the use of a coupling agent and a catalyst. It's also known for the crystalline substituted urea compound that is formed in the process. So carbodiamides are functional groups that vary in structure but maintain one key shared component of two nitrogens double bonded to a carbon. You can see this in the structures of DCC, DIC, and EDC shown on the left, where they all contain the central part. This component participates in the Skeglich esterification, which is why multiple carbodiamides can typically be tested despite their varying structures. Additionally, we explored synthetic pathways implementing uranium coupling reagents. This reaction results in a byproduct of tetramethylurea, and of the uranium coupling reagents, we are testing HA2 and HBTU, known for their quick reaction rate and efficiency.
Additionally, we explored the use of mixed anhydrides for esterification. Yamaguchi esterification uses 2,4,6 trichlorobenzoyl chloride, which is air sensitive and a smoking liquid. You would have to constantly monitor the temperature of the reaction, leading to its limited practicality. Sheena esterification uses 2-methyl-6-nitrobenzoic anhydride, or MNBA, which is a powder. It's easy to scoop and weigh, and it's simple to dump and stir the reaction.
So let's look at the Sheena mechanism. First, triethylamine reacts with mycophenolic acid. The lone pair on the nitrogen attacks the carboxylic acid, breaking the OH bond. The electrons in that bond then move towards the carbonyl, causing the electrons in the carbon-oxygen double bond to move towards oxygen, as it's more electronegative. Protonated triethylamine then leaves, resulting in a carboxylate ion. This then reacts with MNBA. The negative charge on the oxygen comes down into the single bond, causing the carbon-oxygen double bond to then attack one of the carbonyls on MNBA. This forms a tetrahedral intermediate, which quickly kicks off a 2-methyl-6-nitrobenzene carboxylate ion to form a mixed anhydride. This anhydride reacts with DMAP. DMAP selectively attacks the first carbonyl because the second carbonyl is shielded by the presence of the methyl and nitro groups, causing steric hindrance. This then forms another tetrahedral intermediate, which rapidly collapses. The collapse forms another 2-methyl-6 carboxylate ion, an acylated DMAP. Then our ester tail, 4,2-hydroxyethylmorpholine, reacts. The lone pair on the oxygen attacks the carbon attached to the acylated DMAP. This forms another tetrahedral intermediate, which collapses and kicks off DMAP. DMAP then takes the proton from the intermediate, leaving us with our desired product, mycophenolate mofetil and protonated DMAP.
So during this project, we utilized the technique called nuclear magnetic resonance, also known as NMR, a powerful analytical method used to determine the structure of molecules. It works by detecting the magnetic properties of certain atomic nuclei, such as hydrogen or carbon. So when we were running an NMR, we first place a sample in the strong magnetic field, causing the nuclei, for example, in our case, hydrogen, to align either with or against the field, forming two energy states. And next, a radio frequency pulse is then applied, and causing the lower energy nuclei to precess. And as they relax back to their original state, the electrons emit a decaying signal called a free induction decay, also known as FID, which reflects their magnetic environments. And since the FID is in the time domain, a Fourier transformation is used to transform it to NMR. So once we have acquired an NMR spectra, we then have to interpret the data. So each peak in the spectrum represents a distinct proton environment, meaning that chemically non-equivalent hydrogens will produce separate signals and such forth. So the number of peaks within a signal also often follows the n+1 rule, where n is the number of neighboring hydrogens. So if a hydrogen has two neighboring protons, the signal will be split into a triplet. So the chemical shift or the position of each peak along the x-axis in ppm, electronegative atoms such as oxygen or chlorine can de-shield nearby protons, pulling electron density away and shifting their signals downfield towards the left. For example, in the example I have on the right, in dichloroethane, the proton near the two chlorine atoms is more de-shielded and shows up at around 5.8 ppm, while the more shielded protons appear near 2.6.
This is a structural comparison of MPA and its prodrug derivative mycophenolate mofetil. The hydrogens highlighted in red correspond to a diagnostic peak on NMR for MMF, as it does not overlap with MPA peaks. It also appears more downfield compared to the peak corresponding to the same two hydrogens on just the 4,2-hydroxyethylmorpholine ester substituent. In this NMR, you can clearly see the MF diagnostic peak, the triplet circled in red. And this peak does not appear on MPA.
So what is QNMR? It's an analytical technique used to determine concentration and purity of product. You combine some of your reaction with an internal standard whose peaks do not overlap on NMR with your desired product. Based on how many moles you have of your internal standard, you are able to determine the moles of product and consequently the yield of your reaction. So on the top, we have mycophenolate mofetil, and on the bottom, we have our internal standard of dinitrobenzene, and on the right, we have our combined QNMR. You can choose any strong peak from your compound and internal standard, and these will be your diagnostic peaks. Shown here is our diagnostic peak for mycophenolate mofetil, the triplet. And our diagnostic peak for dinitrobenzene is the only peak, it's singlet. So here we have shown how dinitrobenzene and mycophenolate mofetil do not overlap in their peaks, and this allows us to perform quality QNMR analysis. On the left is our yield equation for calculating, where N is the number of moles, I is the integration value, and capital N is the number of protons. It's important to know how much internal standard you have, because this plays an important role in setting up the molar ratio in the equation. For this QNMR, we weighed out 17.4 milligrams of 1,4-dinitrobenzene, which is around 0.001 moles. Now we look at the peaks on our NMR. First, we look at our mofetil diagnostic peak. Because it's a triplet and the splitting pattern of NMR peaks follow the n+1 rule, we know that this triplet represents 2 protons. Then, we substitute the triplet's integration value, shown in green, into the equation. Integration refers to the area under each peak, which is directly proportional to the number of protons contributing to that signal. So because 1,4-dinitrobenzene is a para-dinitrobenzene isomer, the two nitro groups are opposite each other on the benzene ring. This arrangement creates a plane of symmetry that makes all 4 remaining ring protons chemically equivalent. This means that the single peak on dinitrobenzene represents these 4 protons because they are all chemically equivalent. So then we take the dinitrobenzene peak and look at the integration value and substitute it into the equation. Next slide. We then solve for the moles of our product, which turns out to be around 0.48 millimoles. We multiply by the molecular weight of our molecule to calculate its amount in grams or milligrams. Typically, this method is used to calculate yield, where this value would then be divided by our theoretical yield to calculate yield percentage. QNMR is a more accurate way of calculating yield compared to isolated and purifying product and then weighing it out, because of yield loss during column chromatography in numerous transfers.
To conclude, we have optimized a scalable and atom-economical two-step one-flash monosilation of MPA to enable the multigram scale synthesis of an important precursor to mycophenolic acid prodrug derivatives. We also optimize a one-flash synthesis of mycophenolate mofetil using mycophenolic acid without intermediary purification.
We would like to thank our past and present project members, as well as our advisor, Dr. New, for their guidance and their support throughout this project. And finally, we'd like to thank ASRP for making this research possible. Thank you.